this WhatsApp groups, and I found this also contains a lot of knowledge on which are not known to us, hitherto unknown to all of us. So it's a really a very good experience to get unrevealed of that hidden treasures of
Camera.
science and technologies and educations. So with these things, I once again welcome Professor Mishra in this particular programs. Professor Mishra, welcome and very good afternoons. So now I hand over the session to you.
Thank you, Dr. Sarkar. Am I audible?
Yes, your particulars.
Okay. Please see.
Audible.
I am trying to share my slides. Please see whether they are coming or not. Is the slide visible?
Yes, it is
Yes, sir.
visible.
Yes, sir.
Okay. Okay. Thank you. Thank you. Good afternoon, everybody. We'll continue from where we left last time. That is the basic knowledge of mathematics. From that, we'll go to little bit of advanced knowledge that was existing in India or in Bharat. We last time stopped at Bakshali manuscript. So today we will start with Aryabhatta, and particularly I will be concentrating mostly on Aryabhatta. Now he has written six books, out of which only Aryabhatta is available to us now. This is very unfortunate that we have lost. Other books could not be preserved somehow or something. This was available in some library in Karnataka. The original Aryabhatta was available in Karnataka, and somehow it has been translated. People have tried to read it and understand it. And in this Aryabhatta, he gives some information in the beginning and in the end. In the beginning, he gives information about from where he comes from. That he mentions that Kusumapur. Kusumapur is present day Patna. Yes, present day Patna is called Kusumapur. Because when Bhaskara, he uh, translated and gave explanation on Aryabhatta, he said it to be Pataliputra. Kusumapura is the Pataliputra. Aryabhatta, in his Aryabhatta, mentions clearly that in the book, what he is going to write is the knowledge existing and reward or yes, existing and reward by the people of Kusumapur, which means whatever is written in Aryabhatta is not new. Aryabhatta has given the pre-existing knowledge he has written in the form of a book, and he has added his own things there, or his um, brilliance is there to be seen. So his contribution is there, but in addition to his contribution, most of the contributions were pre-existing, which means in India those knowledge were available before Aryabhatta. What we do is we usually say, but or to us it has been told that Aryabhatta invented zero, which is completely wrong. Aryabhatta did not invent zero, he used zero. In zero was much before this, as we have seen. If Aryabhatiya is written at 499 current era, Vaksali manuscript was around 260, 280 current era, and Vaksali manuscript used zero, means zero was before or zero predates Aryabhatta. Similarly, decimal system. I, the Vaksali manuscript used decimal system, so that also predates Aryabhatta. Aryabhatta has codified them properly in Aryabhatiya and other books. That much we can say. This Aryabhatiya, this book Aryabhatiya, it has four parts. Gitikapada starts with Gitikapada, which has 13 verses. In this, he mentions the schemes of representing numbers in his way, not the way that we know, that we'll see later. Then value of different parameters which are necessary for calculations in astronomy. These are given in 13 verses in Gitikapada. Then there is Ganitapada, which has 33 verses. This contains mostly mathematical formulae and different techniques used in astronomy. These include squaring a number, finding the square root, finding the cube or cube root, etc. We'll see some of them. Then Golapada. Golapada has 50 verses. It is discussing about the shape of the earth, source of light, calculation of eclipses. These are discussed there. So we will not go to Golapada. We will confine to Ganitapada mostly. Then Kalakriyapada. Kalakriyapada has, no, Kalakriyapada is third. Golapada is last. Kalakriyapada, this gives a geometrical picture uh, which implies the computational process that he used. So, with this introduction to Aryabhatta and Aryabhattiya, we will proceed. Now, let me make it very clear that the Aryabhattiya is written in such a manner that if we read it, it is extremely difficult to understand unless one is proficient with the language Aryabhatta used. Aryabhatta used his own language. It is not only Sanskrit, he has developed his own grammar, his own meters like hymns, etc. So it is difficult to understand them. It requires a commentary by somebody who has understood it. So most of these, what we are going to discuss, are from Aryabhattiya Bhashya, developed by Bhaskaracharya and others in the latter period of Aryabhatta. These are not exactly from Aryabhattiya. Now in Aryabhattiya, uh, as people attribute zero and place value to Aryabhattiya, so let us see what is there in Aryabhattiya about zero and place value. This sloka we had seen last time also, here also we'll see the last part which I have highlighted, Sthanam Dasagunam. So which means in powers of 10 he is describing this sloka. So 1, 10, 100, etc. in powers of 10. Now, if he is describing it in powers of 10, then Bhaskara, while giving his commentary on this sloka, he says one must ask at this point what potential do these notational places have? Notational places means one becomes 10, then one becomes 100. So, what is the use of this? Then he goes on to explain this and answer this. He says the potential that one and the same entity, which is one symbol, one, a symbol for one, that can connote one, that can connote 10, 100, 1000, etc. Once this potential is established, it is easy for the traders to conveniently tag prices to their commodities, which means this is useful commerce. Useful in commerce. In ancient India or ancient Bharat, commerce was commerce got very high priority. We said Banijye Basati Lakshmi. So commerce was very important in that society. So it is important for the commerce next. Now we said place value. Now what is place value? Let us try to understand it, particularly if there are students. Now suppose we have 1 lakh rupees. If 1 lakh rupees is with a businessman like Ambani, value is 1 lakh. But in the position that Ambani is there, its value is very small to him. If it is with a film star, then the value is slightly more compared to the businessman or a business tycoon like company. If it is with some corporate people, corporate person who is working in a corporate employee, its value is much more. If it is with a shopkeeper, it is still more, and if it is with a labor, daily labor, it is very high. So depending on which position the person is, the value amount is 1 lakh, but it's depending on the position, its value will be value. Now, if we convert that to numbers, let us take a number 3. If it is in place 1, its absolute value is 1, positional value is 1. If it is in place 10, absolute value still remains 1, but positional value is 30. So that way it keeps on increasing as you keep on moving towards left. And the number numeral 3, let us consider this same numeral. Then it has an absolute value which is fixed. It has positional value which varies with the position. So 3, 30, 300, etc. Then there is another value which is called directional value. We'll discuss it later. Directional value is it can be positive or negative. So these are the 3 types of values. Next. With that, let us come to what Aryabhatta has given in his Aryabhatya. He has given an algorithm for finding the square root. For finding a square, there is an algorithm, but for finding the square root, I thought this will be more useful than so I get this algorithm. So what we do here is we mark pairs of notional places as Varga and Avarga. Varga is from you look up from the right side towards left, all the digits. The rightmost digit or the least significant digit, that is Varga. From that place, that is place 1. So from that place, all places are Varga, even places are Avarga. But first count the number of digits. If the number of digits is odd, then the most significant digit will always be Varga. If the number of digits is even, then the most significant digit and the immediate next digit to it, these two will form a Varga. Then what we'll do? Subtract the greatest possible square from the from the last Varga, which is on the left side. Then write down the square root of the subtracted number in the result place. Bring down the next Varga number on the right side of the subtracted value. Divide the number by twice the square root, and remember that the remainder should not be negative. Then bring down the next Varga number of the right side, and then repeat the process till all the digits are adjusted. Example, suppose we want to find out the square root of 83521, 83,521. So first group it into Varga, Avarga. 1 is Varga, 2 is Avarga, 5 is Varga, 3 is Avarga, 8 is Varga. And now on the leftmost side or MSB, most significant digit is 8. So we'll subtract 2 square because 3 square is more than 8. So 2 square will subtract. So subtract 2 square is 4. So that will subtract, that will leave us 4. And then result is 2. Now, this 4 is there, the remainder is 4. Take down abargo. Abargo is 3. So 43. Now, this is 43 is to be divided by 2 into 2. 2 is there. Multiply it with the result. Result is 2. That red you can see. 2 is the result. So, in the red, I have marked it. So, 2 into 2, that is 4. Now, if we subtract, divide 43 by 4, then our question should be 10. But I have taken here 8. Why I have taken it here 8? That will be clear now. So if we take it to be 10, then the remainder will be 3. Then burger that will bring down, that will be 5, 35. Then that will be subtracted from 10 square, because this quotient is becomes 10. So 10 square is 100. 100 cannot be subtracted from 35. So 10 cannot be there. Then you make it 9. If you make it 9, then again it will be negative. So I have made it 8. So this much you have to apply your mind. So if we make it 8, it is 32. 11 is remainder. 5 comes down from the burger place. So 115. So 8 square is 64 is to be subtracted. Once you make a square, then put it in the result part. So that becomes 28. 2 after that you have put 8, 28. So 115 subtract 64, 51, bring down 2. So 5, 1, 2. Then divide it by 2 into 28. Whatever is the result, result is 28 now. So 2 into 28. So that gives us, when we are dividing by 2 into 28, which means uh, 56, 512 divided by 56. So take it 9. 9 will be the question, 504. So take the difference. Then we have 8 as the remainder. Bring down 1. So 81. Subtract 81. Then subtract 9 square is 81. So 289 is the result. So this is how to find out square root. Next. Then he gave an algorithm for finding the cube root. So again here, instead of grouping in 2, now you group in 3. One is called Ghana, cube is Ghana. So one is called Ghana. Ghana is the least significant digit. Then Ghana 1, then Ghana 2. So Prathama Ghana or Dutiya Ghana. Ghana 1, Ghana is A1, Ghana 1, then Dutiya Ghana is Ghana 2. Now remember that if we have n digit number, then the cube of that number will be greater than 3n minus 2 but less than 3n. So using this, you group them into three digits from the right hand side, go move towards the left side. Next. Follow the same principle as in case of the square root. But here what you will do is, instead of multiplying by 2, here we will multiply by 3. So what we'll do, I'll give one example. Look at this example. So last Ghana place is 1. Subtract cube. There we are subtracting square, here it is cube. So subtract cube. Cube for 1 is 1 cube. So result is 1. 1 minus 1 is 0, remainder. Then bring down 4. Then divide this 4 by 3 into 1. And this 3 into 1 square. So whatever is there, this red will be the result square, square of the result. So 3 into 1 square. So that is 3. So 4 minus 3 is 1. Then bring down 0, subtract of the 1 square, what was the quotient? Quotient square into 3 into result. So quotient square into 3 into result. So that is again 3, 10 minus 3 is 7. Bring down 4. 4 is from the Ghana. On Ghana place, we have brought down 4, which is from Ghana place. Once it is from Ghana place, Then subtract the cube of the result. Result is 1, so subtract the cube of the quotient. Quotient is 1, so subtract its cube, that is 1 cube. 1 cube is 1, so 74 minus 1, 73. Then organa 2 is 9, so 739. And then again follow the same principle, 3 into 11 square, 11 is the result, 3 into 11 square. So that gives you 726. Subtract it, 13 remainder, bring down 2, then subtract 2 square into 3 into 11. 2 is the quotient, quotient square into 3 into average. So that is 139, 132. So after subtraction you get 0, bring down Ghana plus 8. 8 for 8, the cube is 2. 2's cube is 8, so 2 cube. So 112 is the result. Next. So these are two things. Then he also gave the formulae for area of planar figures. So first he defined how many types of triangles are there. He defined that there are three types of triangles: equilateral triangle, scalene triangle, and isosceles triangle. Then he said for any of these triangle, the area is the product of the perpendicular. Perpendicular means which is dropped from the vertex to the base into half the base. That gives the area. So this is well-known formula that we know today, but he also has given this formula. Next. Then he also said that suppose you don't know the height or the perpendicular perpendicular. If you don't know the perpendicular, then you have to find out the perpendicular first. For that, he says that find out the abada. Abada is equal to half bhumi into a difference. Now, what is a difference? A sum is, you look at the figure, in the figure, A sum is equal to A. A is the B side BC. So A sum is equal to A, which is BD plus DC. A difference is BD minus DC. Now, if look in this triangle, C square minus B square, C square means BA square, and B square means AC square. So C square minus B square is equal to BD square plus B square minus AD square plus B square. That is equal to BD square minus AD square. So that we can write as BD plus AD into BD minus AD, which is C plus B into C minus B. C plus B is a sum, C because BD is C, BD plus ADC, that gives us C plus B. So that is a sum into C minus B is a difference. So a difference now we can write as CB plus C plus B into C minus B by A sum. Now that we can write as C plus B into C minus B by A, because A sum is equal to A. From that we write this. Then abada is equal to half bhumi plus minus A difference. Now once you know abada, then you can find out P. What is P? P is equal to square root of Karna square minus abada. Karna is BC or AC. That is what is the Karna. Next. Then he gave the area of other plane figures like circle. For circle, he says that the area is half the circumference into semi-diameter or radius, which is pi r square. In today's notation, it is pi r square, but is the formula he gave is half into circumference into radius or semi-diameter. For a trapezium, he said the area if the trapezium is ABCD, then the area is half into F plus B into P. P is the perpendicular difference or perpendicular distance or the difference between the sides BC and AB. F is the side AD B is the side BC. This formula is also well known today. Now, with this formula, next, he gave a general rule for finding the area of plane figures. Now, look at the trapezium. If you want to find out the area of a triangle in the trapezium, make f is equal to 0. If f is equal to 0, then a and d coincide, so it becomes a triangle. So put f is equal to 0, that is half into b into p. Now, if it is a rectangle, then make f is equal to b. If f is equal to b, this becomes a rectangle. So, for f is equal to b, if you put f plus b, f is equal to b is 2b. So, half into f plus b is b, b into p. So, that gives you rectangle square. Similarly, for circle, he says that the semi-diameter, take it as a length, and semi-circumference, take it as the breadth or height, which constitute an equivalent rectangle. Find the area of the rectangle. Next. Then he worked on finite series. This we know from our school days, 1 plus 2 up to n. If we are adding n numbers, the sum is n into n plus 1 by 2. This he gave. Also, he, in addition to this, he gave 1 square plus 2 square up to n square. What will be the sum? 1 cube plus 2 cube up to n cube. What will be the sum? That he said that 1 plus 1 cube plus 2 cube up to n cube will be equal to n plus n into n plus 1 by 2 whole square. Similarly, he also gave a series which is in the form n into n plus 1 by 2. That series that he gave. These two, I don't think were available initially in the West, Western people. Then he gave two formula. The first formula gives the uh, mean of the series of n 1 plus 2 up to n. If you take that series, what will the mean value of that series? The first formula says that it will be a plus n minus 1 by 2 into d. If a is the first term, d is the difference between two terms, two consecutive terms. Difference is the total number of terms is n, then mean value is a this. Then and this sum is a plus n minus 1 by 2d into n. So if you consider an arithmetic series, these two he gave two different formulas. Next. Then following him, Narayan Pandit, he said that if 1 plus 2 up to n is represented as V1n, then the sum for V1 r minus 1, V2 r minus 1 up to Vn r minus 1 will be this n into n plus 1 up to multiply this up to n plus r divided by 1 into 2 into r plus 1 or factorial r. So, and these results can estimate the sum of powers of natural numbers. Then came the beauty. The beauty is, suppose we have a number n which satisfies the two equations. Ax is equal to Ra and By is equal to Rb. Both these are equal to n. Then find out what is n, what is x, what is y. Given A, B, Ra, Rb. These are given and all these are integers. You have to find out the numbers which are all integers. N, X, Y, all integers. Given A, B, Ra, Rb as integer, find out this. Now, I am here. What we are seeing is a formula which he calls Kuttaka formula. But instead of Aryabhata's formula or Aryabhata's principle, we will see here the Brahmagupta's principle. And if n is equal to ax plus Ra is equal to by plus Rb, then the remainder terms Ra and Rb, these are they are called chedars. Sorry, Ra and Rbs are called Agraj and Sesaj. A and B are called Chedaj. And if array is greater than RB, then A is called Adhikagrahara or Adhikagracheda. B is called Anagrahara or Anagracheda. Otherwise, it is vice versa. And let us see what he has said. I will show you the example instead of describing the algorithm. Next. Here is an example. You have to solve n is equal to 34x plus 2, which is equal to 13y plus 10. Now, if you look at this, here a is equal to 34 and b is equal to 13. So, b and array is equal to 2, rb is equal to 10. Rb is greater than array, therefore b is the Adhikagra Cheda and rb is the Adhikagra. Now, RB minus array, which is 10 minus 2 is 8. So note this. Then what we'll do is the algorithm says that first divide the adhika, adhikagra cheda by A. So, so 13 is to be divided by 34. If we divide 13 by 34, quotient is 0. So the remainder will be 13. Then divide this 34, that will now 13 will be divisor, 34 is to be divided now. So quotient will be 2, the remainder will be 8. Now 13 will be divided, 13 quotient will be 1, remainder will be 5. This way will continue. What one has to note is the quotients remove except the first quotient. So 0 is to be neglected. Then you look at the quotient. These are 2, 1, 1, 1. So make a table. Volume means table. So in the table, leftmost column is 2, 1, 1, 1. So those four numbers you pass. Then the next number will be, we have to find out what is the next number. Next number in the table is found out by the number of questions, noting the number of questions. If it is even, then this t is to be chosen, the next number t that is to be chosen, so that 2 into t plus 8 is divisible by 3. If it is odd, then it is to be chosen in a manner so that 2 into 8, 2 into t minus 8 is divisible by 3. So that is what we have to do. Now here it is even. So 2 into t plus 8 has to be divisible by 3. So that means minimum value of t is equal to 2. Smallest value of t is equal to 2. So if we put 2 there, so t put it 2, then we have to find the next value. That is called Labdi. So to find that, so 2 into t is 2 plus 8. That gives us 12. Labdi will be 12 by 3. That is 4. So Labdi is 4. So first column is gone. Leftmost column is gone. Then the next column. Next column, what we will do is leave out 4. So t is equal to 2. That will be the last row of the next column. Then the row above that will have 4 plus 2, that is 6. Then similarly, the last row for the next column will be 6. Then above that it will be 6 plus 2, 8. Next row will be 6 plus 8, 14 and 8. Next, once you continue this till you get RU and RA. RU is called Udharvasi and Adhorasi Udharvasi. So this Udharvarashi 36, you get it like this. 14 above that is 2, 14 into 2 is 28 plus 8, 36. So that gives you 36 and 14. Once you get this, then divide this 36 by A. So 36 by A is 34, 36 by 34, that will give us a remainder 2. Once you get that remainder, then find out n. N is equal to the remainder 2 into Remainder is used as y. So remainder 2 into 13 plus 10. That gives us 36, which is the desired number n. So uh, Urdhva Rashi is usually the desired number. Next. Then he gave the solution for linear and quadratic equations. If ax plus c is equal to bx plus d, that implies that x is equal to d minus c by a minus b. Today, this means nothing, but in those days, at that time, this was a very significant problem, particularly in astronomy. Similarly, in quadratic solution, he gave ax square plus bx is equal to c, implies that x is equal to square root of 4ac plus b square minus b by 2a. Now here, this plus minus sign before the square root is missing uh, in Aryabhatta, but later when Brahmagupta dealt with this quadratic equation, he introduced negative also. Next. Then this is about his contribution to geometry, mensuration, and little bit of algebra and arithmetic. Then comes now we'll see the after the basics we'll see a little bit of advanced thing. So this starts with the trigonometry. Don't worry about this Roko. This Roko we'll see later. The what it says is you take a circle. Next, take a circle. If you take a circle, then uh, form a and draw a chord on one side. On one side of the circle, draw a chord. That chord you will call ja. The Shloka says this. This chord is called ja. Half of that chord is called ardhaja. But mostly Aryabhatta and others, they use ja to mean ardhaja. Wherever after this, wherever I use ja, you will understand it is ardhaja. Then from the center you join to one of the end, so draw a line joining one of the end of the ja, that is called karna. Then the portion of the circle or the perimeter of the circle that connects the two ends of the ja is called chapa, which we call arc in English. Now from the ja to the perimeter, if you extend the radius from the center as a perpendicular bisector to the ja, then from the ja to the perimeter is called sara, and from the center up to the ja is called koja. Why it is called this way? Next. It is because like this. If you look only at this portion, it looks like a bow. In the bow, you use an arrow. So the arrow is called usually sara. Arrow is in English, in Sanskrit, it is called sara. Or India and many parts of India, it is called sara. So that is sara. This part is koja, that is ja. Okay. So this information we are going to use later in the trigonometry. Now, trigonometry, we know that father of trigonometry is the Hipparchus in 150 BCE, much before Aryabhatta. What he did is he divided angles to steps. For each 124th step, he tabulated the chords to find out the sines or cosines. Then came Ptolemy. Ptolemy he divided 180 degree into 360 steps. Then he computed the chord lengths. So this is what they have done. Usually they have found out the chord lengths, both of them. In Bharatavarsha, Surya Siddhanta is about 600 BC. Some people can say 600 BC, some people say 400 CE. I don't know because Surya Siddhanta is very old, and it gets corrected every time. So last correction was around 400 CE, current era. So this Surya Siddhanta that gives modern trigonometric functions with sine, cosine. Cosine means it is 1 minus cos theta. Inverse sines, etc. It mentions that ja, for sine it mentions ja, for cosine it mentions cotija or koja. Then for cosine it says utkramaja, and for inverse sine it says otkarmaja. So these were the used in India. For sine it was ja. Then Aryabhatta he gave a trigonometric table of 3.75 degree steps from 0 to 90 or pi by 2. Bhaskara one, he gave sine approximation. Brahmagupta, he gave second order interpolation. Madhava gave infinity series. Now this Jya, when it was Jya is in Sanskrit, when it got transmitted from India to Persia, it became Jiva. Uh, then from Persia it went to Latin. In there they called it Sinum. Then from Latin it came to UK or England. There they call it Sin. So originally Jija. Next. Then Aryabhatta, when he used astronomy, he has to deal with very large numbers. So he developed his own system of numbers, own system of calling these numbers, giving names to these numbers. If you look at this sloka, oh, Makhi, Bhakhi, Fakhi, Dhaki, etc. It looks like a Sanskrit sloka, but there is not a word of Sanskrit except the last word. And so everything is Aryabhatta's own invention. He has invented this, and Makhi means 225. The number 225 he is writing as Makhi. This way he has done it. Now this is called Aryabhatta's alpha syllabic number system, which means he has associated alphabets to numbers. So that is why it is called alpha syllabic number system. Arya alphabetic number system also some people call it. Let us see what is it. He says that you uh, take two categories of syllables, vowels and consonants. In consonants also, you take two categories. One is from ka to ma, which is bargas, and after ka to ma, ja to ha, these are called abargas. And he assigned numbers. If these are vowels, and vowels are associated with uh, are conjoined with sorry yes, vowels are conjoined with these consonants. Then if it is vowel is o or a, it is 10 to the power 0. For Khartoum, for burgers, for a burgers it is 10 to the power 1. So this way the table is given. Below for the burgers, the numbers are for the burgers, the numbers are for ka to ma, ka kha ga ga, ma that is 1 to 5, cha cha ja ja nya that is 6 to 10 that way. But for pa pha ba ba ma it is 20 to 25. And he said that after ma, ja ra ra ba sa ha kya, those will be 30, 40, 50, 60, 70, 80, 90, 100. Then we'll see how it is done, how the numbers come. Makhi. Makhi means ma plus kha plus e. So ma is 25. Look at this from the table. Ka to ma is 25. So ma is 25, kha is 2, e, e is 10 to the power 2 because kha is a Varga letter. It is between ka to ma. So e is 10 to the power 2, 100. So kha and e are added, therefore they will be multiplied. So 2 into 100, 200 plus 25 is 225. Similarly, Vaki will be 224. Then Hakya, it has Ha is 100, and then Ka is 1, Ya is 30. So 30 into 1, 31 plus 100, 131. So you can see the table above. In the table for Maki, it is 225, Bhaki 224, and 131 for Hakya. So that is how this table he formed for the R sign table. Next. Similarly, after Aryabhatta, in the particularly in the southern part of India, in the Kerala, towards Kerala, they developed something called Kottapayadi Sankhya. In the Kottapayadi Sankhya, or Melakataragam names and numbers, so they associated 1 to 9 and 0 with only consonants, no vowels. All vowels are 0. Values are 0. And this table gives those how the consonants are associated with the numbers. Then for each consonant, you will add the number. For example, look at the above sloka. The meaning of the above sloka, if you look at the Sanskrit, Sanskrit meaning is, O Krishna, the fortune of gopis, the destroyer of Demon Madhu, the protector of cattle, the one who ventured the ocean depths, destroyer of evildoers, one with plow on the shoulder, and the bearer of nectar, may you protect us. This is the meaning, normal meaning. But if you use the Katakayadi Sankhya, this for Ga, you have to use 3. For Pa, you have to use 1. So this way you use this number that gives you 31419. This number which is written below in the red, that is the value of pi. Next. Now we have to find out the sine and cosine, etc. So how Aryabhatta found sine cosine? He found it in two ways. One is he used geometrical method, other is he used analytical method. Let us first see the geometrical method, how he used geometrical method. So for geometrical method, he says that he gives a theorem. The chord of 1/6 of circumference of a circle is equal to the radius, which means if you look at the circle, top circle, then OBC, and this is an equilateral triangle. Since it is an equilateral triangle, then and OB or OC, these are radius, therefore BC is also radius. Why it is an equilateral triangle? Because BOC is 60, so other two are have to be 60. Because OC and OB are same being radius, so other two angles are 60, so it is an equilateral triangle. Okay. Then what you will do is, make the quadrant of the circumference of a circle be divided into many parts, as many parts as we desire. Then from the right triangles and rectangles, from those parts, form right triangles and rectangles from those parts, one can find as many arc signs or of equal arcs as one likes for any given radius. If the radius is given, you can find it. And what we'll do is, what he does is, he takes unit radius and he divides one quadrant. Let us take the first quadrant into 24 parts. So P0 to P24 equal parts. He divides them into 24 equal parts. So each part is representing each arc bit of the part is representing theta, which is 90 degree by 24, that is 3 degree 45 minutes or 225 minutes. Now we have to find out r sine I theta for each theta. I is equal to 1, what will be the value? I is equal to 2, what will be the value? What we have to do is look at the bottom figure. Sine will be P by Pn. That is the perpendicular drop from point P onto the base OP0. So that perpendicular will give us the sine, that we know. Why it is r sine theta? Because we know sine theta is equal to P by H. H here is r. So P is equal to r sine theta. So this perpendicular is equal to r sine theta. That is why we do this. Next. So how to do this? Let me explain this. What is r? It is a unit circle. If you consider a unit circle, and its circumference will be 360 degrees. Unit circle means the r into or the radius into unit radius into 2 pi. 2 pi is 360 degree. So 360 degree. So radius r will be 360 by 2 pi. 360 degrees 360 into 60 minutes by 2 pi. Use the value of pi 3.141. So put that, this will be approximately 3438. So R is equal to 3438. That will be equal to a chord which extend 60-degree angle at the center. Then look at the triangle OBC in this picture. Look at the triangle OBC. There BC is equal to R sine theta. That is equal to R by 2. Why it is R by 2 BC? If you look at this, BC is equal to OA. OG is equal to R, OA is equal to R by 2, so BC is equal to R by 2. Okay, so BC is equal to R sine theta or sine 30 degree because total is 60 degree. BO and other side, if you go to the left side of the C, if you join that triangle, that will be 60 degree. Half of that is 30 degree. So BC is equal to R sine theta, which is R by 2, that is 1719. Similarly, in the rectangle OABC, if you look at the rectangle OABC, AB is equal to R sine 60, uh, that is OC. AB same as OC, that is equal to R sine 60 degree because AB is equal to, yes, R sine 60 degree. BOA, R sine 60 degree or R sine of BOA. BOA is equal to 60 degree. So OC, and that is OC is equal to root over of OB square minus BC square. So that is root over of R square minus R square by 2, which is root over of R square by 2, that is 2978. Then that is from R sine 30, which is the eighth one, because we have got 24 angles. So eighth angle I is equal to 8. That means I is equal to 8. We get this 16th R sine 60 degree. 30 degree, from 30 degree we have got sine 60 degree. So from 8th one we got the 16th one. So if you have got R sine theta, from that you can all easily find out what is R sine 90 minus theta. So 30 we have got 30, from 30 we got 90 minus 30, which is 60. Similarly, from 30 we can find sine 50. So here you look at this, BD is equal to cot 60, that is equal to 1780. R sine 30 plus R was 30 degree. So R sine 15 will be half of BD, that is 890. Look at the triangle, look at the picture, it will be very clear. R sine 15 is equal to half BD square. So that is, sorry, half BD, that is equal to 890. Now that way, once you got to 15 degrees, so from 30 you get 60, from 30 you get 15. So this way, if I know R sine theta and R cosine theta, then we can always find R sine theta by 2. In the once you get 15 degree, you can get 75 degree. Next. So this using this method, you can find all the values, all the 24 values. Then what is to be done, that we'll see later. So that is about Aryabhatta's fundamental contributions. Another contribution we'll see later. Then we'll come to Brahma Stupa Siddhanta by Brahmagupta. So he wrote this book. He was after Aryabhatta, and in this book, he gives the definition of integers. He describes arithmetic operations. He gives principles of algebra, geometry, and trigonometry. Next. Now, it takes the concept of negative numbers that was prevailing in those days. Now, we all know Kepler gave us the orbital motion. The orbit of a planet is an ellipse that is with sun at one of its two foci. That is what Kepler said in 1609. But the second sloka of the Surya Siddhanta, it says when the planets are pulled strongly by sun at their Uchchasthana, which is apices, they will have highest orbital velocity, which is called dhanam. Highest orbital velocity is called dhanam, and when they move away, their velocity decreases. That is called runam. So two terms are there, dhanam and runam. High, if you have high value, then it is dhanam, otherwise it is called, if it is low value, it is called runam. So dhanam is the accumulation or wealth or credit. Runam is debt or depletion or returning back. And Sunyam is void or empty or stable state. So from the stable state, if you are accumulating or crediting or you are going away from the stable state, it is dhana. If you are coming towards the stable state, it is runa. And stable state is sunya. This principle was used by Brahmagupta for positive as dhana, negative as runa. These are the transient states with respect to zero or shunya. This using this, he gave little rules of addition, subtraction. Next, rules of addition. There he said positive plus positive is positive, negative plus negative is negative, positive plus negative is difference of their magnitude. Positive plus negative is equal to 0 if they are of the same magnitude. 0 plus 0 is 0. Positive or negative plus 0 equal to positive or negative of same value. Then he gave rule of subtraction. Large positive minus small positive is positive. Negative minus negative, negative. Positive or negative minus 0 equals to same positive or negative. 0 minus 0 is 0. Next. Next. Multiply rule of multiplication. Negative into positive is negative. Negative into negative is positive. Positive into positive, positive. Negative or positive into 0 is 0. 0 into 0 is 0. All these we are using today. Next. Rule of division. Positive divided by positive is positive. Negative divided by negative is positive. 0 divided by positive or negative is 0. 0 divided by 0 is 0. This is ambiguous. This we are not using today. Today we are saying 0 by 0 is undefined. Okay. Now here the concept of positive or negative was used in by Brahmagupta. But when after Renaissance the concept of negative went to Europe, it was very difficult to accept them. I'll give you two examples. One is by Arnold and Pascal. Both of them, they said that suppose one positive one is greater than negative one. If that happens, then if we divide negative one by positive one, we are dividing a lesser number by a greater number. If we are dividing positive one by negative one, we are dividing a greater number by a lesser number. So, and both are negative 1 minus 1. Both sides will be minus 1, which means a lesser number divided by a greater number is equal to greater number divided by a lesser number. This is not possible. Therefore, existence of negative number was questioned. That gave a paradox. And when it went to Leibniz, he said that the margin is too narrow to solve this paradox. It is very difficult to solve this paradox. Next. Then came the era of Euler. What he said is, let us say A is a positive number, greater than 0 positive number. Then A by 1000 is less than A by 100. Up to as you keep on decreasing the denominator, the value will keep on increasing, and as you make denominator 0, A by 0 is equal to infinity. All right. Then the smaller denominator is giving a larger fraction. Now minus 2 is a smaller quantity compared to 0. If minus 2 is smaller quantity compared to 0, then a by minus 2 has to be greater than a by 0, which is infinity. So a by minus 2 has to be greater than infinity. So he also rejected this idea based on this logic. So negative number initially found resistance in Europe because they didn't understand, they could not understand the zero concept that Brahmagupta has understood that we described earlier. Next. Then another contribution of Brahmagupta is solution of the equation uh, of the rational solution of the equation AXY is equal to BX plus CY plus D. Um, Now, for the solution, he said that choose any number p as the star number and obtain the quotient q as the of t, so that BC plus AD by P is equal to Q is equal to AX minus C. If you do this, then X is equal to either C plus Q by A or C plus P by A, and Y is equal to B plus P by A or B plus Q by A. That is the solution he proposed. For example, suppose xy minus 3x minus 4y is equal to 90. He gave this example. A is equal to 1, B is equal to 3, C is equal to 4, D is equal to 90. Write this equation in the form ax minus c into ay minus b is equal to ad plus bc. So x minus 4 into y minus 3 is equal to 90 into 1 plus 3 into 4, which is 90 plus 12, that you can write as 6 into 17. So x minus 4 is equal to 6, y minus 3 is equal to 17, x is 10, y is equal to 20. Now this is not unique, because if you write 90 plus 12 is equal to 2 into 51 instead of 6 into 17, you can also write it as 2 into 51. If I write it in 2 into 51, then x is equal to 6, y is equal to 54. Similarly, you can get many more solutions. Not a unique solution, you will not get unique solution because there are two variables and you have got only one equation. So indeterminate equation, it is not unique. But you get the solutions. All are integer. Remember, these are all integer solutions you are getting, not irrational numbers. And this is called Bhavita problem. This was one problem. Next. Then he also gets another problem called Bhavana problem. In this, he said, suppose n, x, y, and z are integers. N is a constant, x, y, z are variables. Now they satisfy nx square plus z is equal to y square. If this is satisfied, then for this equation, if x1, y1, z1 is a solution, x2, y2, z2 is also a solution, then x1, y2 plus x2, y1 and nx1, x2 plus y1, y2 and z1, z2, they also form a solution. These triplets. X1, Y1, Z1 is triplet, X2, Y2, Z2 is triplet, then X3 is X1, Y2 plus X2, Y1, Y3 is NX1, X2 plus Y1, Y2, and Z3, Z1, Z2. Using this solution, he gave an example. 92x square plus 8 is equal to y square. Then 92 into 1 square plus 8 is equal to 10, because 92x square plus 8 is equal to y square. Y square is a is a square of a number. If you look at 92, nearest square will be 100. So take 100 as the y square. So that is 10 square. That makes x square is equal to 1. So 92 into 1 square plus 8 is equal to 10 square. And so we have got x as x1 as 1, then y1 as 10, and z1 as 8. That we have got. Then use the principle, Bhavana principle. X1 for x2, y2, z2, take x2 is equal to x1, y2 is equal to y1, z2 is equal to z1. There is no restriction on that. Use that principle. That gives us 20, 192, and 8 square. That as a solution. Then take that, divide it, that is not satisfying the equation. So divide it by 8 square, so that gives us 92 into 5 by 2 square plus 1 is equal to 24 square. So I can apply Bhavana here. 5 by 2, 24, 1. There you apply the Bhavana. That will give us 92 into 120 square plus 1 square is equal to 100, 1151 square. So that solves the problem. Next. So now let us compare the contribution from India and West, Bharata and West. Aryabhatta, followed by Aryabhatta, Brahmagupta, etc., they all gave a Kuttaka problem which solves ay minus bx is equal to c, this indeterminate equation, first order indeterminate equation. They solved it. Then that they did in 499 CE. Bassett did the same in 1621 CE. Then Brahmagupta's problem we just saw, dx square plus z is equal to y square, which Bhaskara gave another problem. So Bhaskara gave a challenge, 61 x square plus 1 is equal to y square. If you can solve this in one day, you are a mathematician. That was his challenge. The same challenge, exactly same numbers, was given by Fermat in 1657. Bhaskar gave it in 1150. Current era, Fermat gave it in same problem, exactly same problem in 1657. Then, smallest positive integral solution of 61 x square, this plus 1 is equal to y square, that was solved using Bhavana principle. That was solved to give x and y. These are the smallest values of x and y that satisfy this equation. Then Euler, discovered Bhavana identity in 18th century. Uh, this in this manner. Now, there is a quote by A. Witt. He said, "What would have been Fermat's astonishment if some missionary just back from India had told him that his problem had been successfully tackled there by native mathematicians almost 6 centuries earlier. Because Fermat did pose the problem in 1657, whereas Bhaskara had solved it in 1150. Next. Then I will come to the almost the last part, the a differential equation which comes from the differential calculus that deals with rate of change, and integral calculus that deals with limit of summation of limited series. Okay. Because in science, engineering, technology, we use mostly differential equation to solve our problems. We formulate the problems in the form of differential equation, and then we solve the problems in by solving those differential equations. Whether it is Maxwell's equation for people like me in the field of electromagnetics, or whether it is Schrodinger's equations for quantum physics, or in electron device, etc. Now the question is, who invented calculus? Newton or Leibniz? There was a uh, toggle between these two personalities, great personalities. Who invented it? Somebody said, I have published it earlier. Somebody says, I have derived it earlier, proposed this earlier. And so finally it was decided that both will be credited with the invention of calculus. Okay, let us see that. What happened? Now we were calculating r sine theta using geometrical method of Aryabhatta. Aryabhatta also said that if you find out these 24 values in the quadrant, then you can find out any other value. For that, he gave an analytical method. He said, let us take Bn is equal to r sine nh. H he has already taken 225 degree, which is 2 pi by, pi by 2 by 24, which is pi by 28 to 25 degrees. Then he said R sine differences. This is the slope. I am explaining the slope. It's very difficult to understand this slope. So R sine difference is delta n. Let us write it as Bn plus 1 minus Bn. Second difference he gave us delta n plus 1 minus delta n. This he actually gave. This is equal to minus Bn into delta 1 minus delta 2 by B1. Now, in the SOCO actually, he mentions that you take the first difference, then you take the second difference. In the second difference, right hand side, you will get. In the first difference, whatever you get in the right hand side, you take the second difference of that. On the right hand side, you will get the first difference, which is you start with sine, take two differences, you will get again sine. So sine to cosine, then sine. So from this, hopefully you are getting fragments of the differentiation. Sine, differentiate it once, you get cosine. Again, differentiate it once, you get back sine. So the that you get that fragments of differential calculus you get. Then you also get the fragments of integration or solution of differential equation. What is the practical way of solving differential equation? Unless these are you have a specific problem, then for which um, closed form solutions are available, you will not get a closed form solution for a differential equation. All practical problems, all research problems, there we use some sort of numerical technique, be it finite element method, be it finite difference time domain technique, be it method of moment, anything. But there you have to take the difference. So design differences, he is saying the difference table or finite difference technique, that is what he is mentioning here. Without knowing that what he is mentioning, we do not know whether who proposed finite difference technique. We always give credit to the West for the finite difference technique, but he is proposing that for the finite difference solution of differential equation. Okay. He approximated delta 1 minus delta 2 to be 1 degree because delta 1 we found out 225, delta 2 224. So that is 1 degree. Now how it is 225? First one is why it is 225. There also he has used the approximation that sine theta is approximately theta when theta is very small. So 225 minute is very small, so he took it as 225. So delta n plus 1 minus delta n is approximately minus bn by 1. Bn is equal to a sine nh. Therefore, second difference gives you sine. Now, if I use that in the difference equation, I get r sine n plus 1h minus r sine nh is equal to r sine nh minus r sine n minus 1h minus r sine nh by r sine h. If you look at this equation, this is a recursive relation. Perhaps this is the first recursive relation that we know. Next. Then, if you use this recursive relation to generate that table, sine table, R sine table, first five or six values you will get correct values for the differences. But after that, there will be error, visible error. So to correct that, Bhaskara later gave this, refined this recursion relation into this form. And whereas Aryabhatta used 2 into 1 minus cos theta, approximately 1 by 225, because 2 into 1 minus cos theta gives you this value 0.0042822, while exact value is this 1 by 225, uh, is approximately equal to 0.00, then force. Next. Then after him, after Aryabhatta, Brahmagupta said that there is not necessary to go up to 24 divisions. We can use, instead of 225 minutes, we can use 900 minutes, and with only five values: 15, 30, 45, 60, 75. So 0 and 90 are constant. In between, only take five values. Then use this interpolation formula. He gave this formula. In this Shloka, he gives this formula. R sin NH plus delta is equal to this, the top one, that you can algebra, with simple algebra, you get Bn plus delta by H of delta n plus 1 plus delta by H into delta by H minus 1, delta n plus 1 minus delta n by 2. He gave this formula. Now, if you look at this, R sin NH plus delta is equal to Bn plus this, the lower last line. Try to remember what it represents. Next. It represents something like this. Fa plus Xh is equal to Fa into this, which is Newton's Stirling interpolation formula much before the formula came into existence. This was given by Brahmagupta. Next. Now this I will skip. This is an example because we are we have 10 more minutes, 10 to 15 minutes. So I will skip this examples. Using this example, what he does is he finds out the value of sine 67 degree, starting with sine 60 degree. Then Madhava, instead of using these the difference formulas, he gave a series. Madhava mostly worked with, Madhava is from the Kerala school of mathematics. He mostly worked with series. So he gave series for r sine theta. From r sine theta series, you can find sine theta. This S is the for the arc length. So from that you find out r sine theta is of this form, theta minus theta q by 3 factorial. That form, that is called the Newton sine series. Then he gave the series for r cos theta. From that, you, because r cos theta is r minus r cos theta. So from that you can find out what is r cos theta. It is 1 minus theta square by 2 factorial cos theta 4 by 4 factorial. That series, this is called Newton's cosine series. But this came much after Madhava. So Madhava earlier gave this series in India. Next. Then we have to say something about Bhaskara. Since we are considering calculus, I have to say something 2 minutes on Bhaskara. He gave a geometrical proof of sine y dash minus sine y is equal to y dash minus y cos y. This he proved using geometry. What he used is, he used a tangent to a circle to find the Tatkalika Bhagyakhanda, or the sign difference. So I found out the sign difference geometrically, and from that he proved this formula. So sign differences he used first. Then you introduced the concept of Stulagati. Stulagati means velocity. Tatkalika or Sukmagati, which is instantaneous velocity. For instantaneous velocity, he has to use the concept of limit that we use later in calculus. And Bhaskaracharya used the concept of limit for computing the instantaneous motion of a planet. Instantaneous because they were working in the field of astronomy. So they were observing the motion of planet. So for computing the instantaneous motion of a planet, the time interval between two successive positions of the planet was no greater than a truti. Truti is a unit of time which is 1 by 33.750 seconds. And so that you can imagine how small is the time. So this measures the velocity. This was expressed in his infinitesimal unit of time. So delta t goes to zero. So limit in the limit delta t goes to zero. So that limit concept he introduced in Tatkalika or Sukmagati. Then he was also aware that when a variable attains the maximum value, its differential vanishes at the maximum value. He showed that when a planet is either at its farthest from the Earth or its closest, either of the two points, farthest point or the closest point, the equation of the center will vanish. At these 2 points, the equation of the center will vanish. And from that, he concluded that in between these 2 points, there is some intermediate point or some intermediate position where the differential of the equation of the motion is zero. Or sorry, differential of the equation of the center is zero. Now we studied in calculus if there are a function is zero at 2 points, then in between those 2 points there exists another point where the differential of the function vanishes, which we call the mean value theorem or the Rolle's theorem that he gave. Bhaskara gave Rolle's theorem came in 1691, much before that Bhaskaracharya gave this theorem. Next. Then he found out the area and volume of a sphere. For the volume, this Soko gives the area of a volume of a sphere. What I will describe here is the area, surface area of the sphere. What he did is take the sphere, divide upper part from the center to the upper part into 24 parts, each of 225 minutes, and take one strip, elongate it. If you cut it and elongate it, you will get a trapezium. Find out the area of the trapezium, then add all the trapeziums. Area of all the trapeziums, you will get it, which is effectively the integration. Next. Then I will come to the pi. That with this we will end. Pi in ancient India or ancient Bharat. This part, this is a paper by Charles M. Weiss, who was staying in Kerala for some time while serving the British India, and he came in contact with the people in Kerala, learned that they know mathematics. From them, he learned the value of pi, how they are calculating pi, and he tried to publish a paper. He submitted the paper in 1824 to Royal Asiatic Society of Great Britain and Ireland in those days. Transactions of Royal Asiatic Society of Great Britain and Ireland. Now it is called Transaction of Royal Asiatic Society. But the paper was not published. It was hold, and they tried to find out whether the knowledge of pi has, is indigenous to Indians or Indians have got it by some means from Europe. So after 10 years, in 1834, they published this paper. In 1833, which died, this paper was published, and his brother was intimated that the paper has been published after 10 years. They didn't publish it for 10 years. So, how much they value their contribution compared to others' contribution, that we can find from this. Next. This is the paper. The right hand side is the paper. Now in India, next, um, Aryabhatta first started to find out the value of pi. So this involved approximating a circle to a regular polygon and increase the number of sides of the polygon. So as you increase the number of sides of the polygon, the sides will align with the perimeter of the circle and you will find out what is the perimeter of the polygon, perimeter of the circle. Once you know the perimeter of the circle, you know the diameter of the circle, take the ratio and you get pi. Next. So he gave this formula. Add 4 to 100, multiply that with 8, and to that add 62,000. This is approximately, remember this word, approximately. Asanna. Asanna means approximately. This is approximately the circumference of a circle whose diameter is 20,000. So if you put this, pi is equal to, take the ratio, so the ratio is pi. Pi is equal to 4 plus 100 into 8 plus 62,000 by 20,000. So that gives 3.1416, and he was very much aware that this is not the exact value, this is the approximate value. One cannot find the exact value of pi, it is an irrational number, that he was very much aware in those days. Now, this was improved later uh, in the by Madhava, uh, and Madhava said that pi is not this value, but use this 28274 triple three double eight two double three divided by 9 into 10 to the power 11. So he get a better approximation than uh, uh, Aryabhatta. Now here, this sloka, we have seen two types of uh, um, alpha syllabic numbers. One is by Arya, other is Katapayadi. This one is called the Bhuta Sankhya method. In this, if you look at the sloka, it says Nava Nikharva Mite. So 9, then Nikharva is 10 to the power 11. But in the beginning, Vibudha, Netra, Vibudha is 2, Netra is 2. So this way, Netra means 2 eyes. Similarly, Rama means 3 Ramas. Parshurama, Ajodhya Rama, Balarama. So this way, you assign the numbers. So it is difficult to decipher these things unless one is very aware of what is being taught or what is being said. Next. Then Madhava, these are two slokas defining the pi. First slokas gives Paridhi is equal to 4 times base. So Paridhi means perimeter is equal to 4 times the diameter into 1 minus 1 by 3 plus 1 by 5 minus 1 by 7. That series, which is was given by Madhava, and it was rediscovered by Leibniz in 1674. Then the second sloka gives S is equal to, S means the chord, the arc length. Arc length is equal to jab r into jab I koti minus r by 3 into jab I koti q plus r by 5 jab I koti 5 minus this series. So that you can write S is equal to r into theta. So if you write that, and then you put j by koti square is equal to 1 by 3 for theta is equal to 30 degree. If you take 30 degree, that is when the arc is diameter by 12, then that gives you theta is equal to 30 degree, put that 1 by 3, then C is equal to, C is, S becomes C is equal to 12 R by root 3 into 1 minus 1 by 3 into 1 by 3 plus 1 by 5 into 1 by 3 square. So and that you can write as root over of 12 d square into this value. So this was rediscovered again by Sharp in 1699. So these were given by Madhav. Now those were approximate values, and those series were so long, their convergence was very slow. So actually, people observed the process, measured the process. From that, they developed mathematical models, either empirical models or physical models. Then they used refinements. With time, they refined those models to get back to newer models or better models. This is the process that was used in Bharat earlier. Now, how this refinement is done? Next. Now, Madhava was brilliant enough to understand that this series is converging very slow. The first series, 1 minus 1 by 3 plus 1 by 5, that series is very slow. So one will get bored in adding those things and you will not get it. So he said that go up to certain point, there is stop and add this correction term. Minus 1 to the power p plus 1 by 2 into p plus 1 by 2 divided by p plus 1 square plus 1. Add this correction term, you will get a very good value. In the convergence will be good and the approximation will be good. So this one, let us call it 1 by AP. Then he gave a second correction. The second correction is given in the second slope. And if you look at this correction, they can 1 by AP can be expressed in this form. 1 by AP is equal to 1 by 2p plus 2 plus 1 by 2p plus 2 plus 2 square by 2p plus 2 plus 4 square by 2p plus 2. So this way you continue. Now if you take p is equal to 1, the continued fraction becomes 2 by 4 minus pi is equal to 2 plus 1 by 2 plus 2 square by 2 plus that way. This is same as the, or this is equivalent to or comparable to Brocknos, who gave 1656 the continued fraction pi for pi by 4. Next. Then this is, I think this is the last one. Okay. Then C is equal to 4d into 1 minus 1 by 3 plus 1 by 5. For that series, what we'll do is we'll add and subtract one or some terms. So 1 minus 1 by a1 plus 1 by a1. So 1 by a1 cancels. Then plus 1 by a3 minus 1 by 3 minus 1 by a3. So 1 by a3 cancels. So this way you rewrite the series. If you rewrite the series, then if AP is equal to 2p plus 1, then put the value of p is equal to 1, p is equal to 2, etc., you get the second series. C is equal to 4d into 3 by 4 plus 1 by 3q minus 3 minus 1 by 5q minus 5. This series you will get. Now look at this series and compare it to the original series. Original series was 1 minus 1 by 3 plus 1 by 5. So that one was in the powers of 1. Denominator was powers of 1. Here the denominator is in powers of 3. So this is a faster converging series. Then if you use this series, you take this series, then use this identity 4 by 4n minus 1q minus 4n minus 1. Because if you take n is equal to 1, this is 3q minus 3. Similarly, minus 4 by 4n plus 1q minus 4n plus 1. If you take n is equal to 1, it is 5q minus 5. So for the second term and third term of the second series. So that is equal to 4 by 2 into 2n square minus 1 square minus 2n square. If you use this, this is transformed. This series is again now transformed to a series which is converging with fourth power in the denominator. So it is still faster converging. Now if you take AP is equal to 2p plus 1, sorry, 2p plus 2 plus 4 by 2p plus 2, then this is converging as the fifth power of the series. So faster convergence is again available. Next. So let me summarize pi. Uh, the first is Aryabhatta gave a formula without using pi. Then he gave a formula from which we can find out pi. Then came Madhav Madhava gave the infinite series for pi, fast infinite series for pi, which is equivalent to integration by part. And this was, you can say, one stepping stone for fundamentals in calculus. Oh, and this is why the Jyotisha is the root of calculus. In India, we worked on Jyotisha or astronomy, and this was reinvented by Leibniz. Now it is called Madhava Gregory series by some people. Next. Finally, it is the pi value was given by Ramanujan, and this series is very fast converging, and it gives up to 17 million decimal points, correct? Up to 17 million decimal points. And these are some of the comments by different people. Wales comment we have seen. Then Manjul Bhargav, Fields medalist, he has said several verses in Sulva Sutra make it clear that Sulva authors knew why theorem is the true. Swedenborg, he said Greeks were not the inventors of the plane geometry. Rather, it was Indians. At least this was the message that the Greek scholars saw in Thibaut's paper, and they didn't like it. If the Indians invented plane geometry, what was to become of Greek genius or of Greek miracle? Most of the refutations of the Indian work were mere haughty dismissals without any logic. They dismiss it. Anyway, the damage has been done, and the Sulva Sutras have never taken the position in the history of mathematics that they deserve. Uh, Similarly, Laplace, he had said the ingenious method of expressing every possible number using a set of 10 symbols emerged in India. The idea seems so simple nowadays that its significance and profound importance is no longer appreciated. And finally, Amartya Sen, the Nobel laureate, in his argumentative India, he says, as it happens, despite the richness of Vedas in many other respects, there is no sophisticated mathematics in them, nor anything that can be called rigorous science. So he criticizes the Veda, but he again after that he says there was, however, much of both in India in the past millennium of CE. And these are some of the books which one can refer next. With that, let me stop for today. And if you have any comments or questions, I'll be happy to respond.
Yes, wonderful lecture, and unfortunately, there had been very few takers, and well, I'd be happy if this kind of, I mean, findings uh, is uh, uh, is made uh, widely publicized, and I would be more happy that if this kind of lecture is delivered in a wider platform, catching the attraction of more, I mean, who's who in India. This is my
Right.
comment.
Yes, sir. Yes, I agree to that. And hopefully, we will work on this. People will start working on this. This particularly the younger people, younger generation will be interested in our heritage, and we start working on this. what we have lost and how we can combine what we have lost that with what is the progress now is being made. So if you do that, then maybe we can progress at a faster rate compared to the present rate of progress. Maybe that will be possible. If we can establish a link between the past and the future.
Hello, sir. I feel some a person of the rank, prime minister or somebody, should hear this lecture. Somehow, you should get a Batma award. More than that, we will try to arrange this lecture through Veda Society also. Professor Prasanta Basu is here. I already heard he's meta middle class. Maybe I will ask privately, how did you manage to go to this much ocean level of other subject? So I wish after he completes his book writing, Professor Basu also will hear. We will arrange a class. Definitely more than 40-50% will be there. Vacuum Electron Devices Association. Through that also, we'll make the country to know or world to know. I really surprised how you came out from fractal antenna, FTTD techniques. From there, how did you manage to come to this side? Not manage, how you made this miracle? I really don't have words. As great Prasanta told, we are very fortunate and I really wonder, maybe some other day we'll have one lecture in a bigger society of how did you change the domain and doing. I really do not know how you prepared PPT like a textbook. Anyway, I will ask separately, sir. Nothing
Sure,
other than showing my namaskar to you.
sure.
So if there are any other comments or queries or any other things from the other attendees. Okay, so if there are no other comments, I must say that my stock of vocabulary and word is limited to express our gratitude to Professor Mishra for these wonderful presentations and awareness generations to the faculties and the participants, the students, research scholars of these faculty development programs. But as we are seeing that these aspects of our traditional Indian science, technology, mathematics, etc., has not reached to its level to attract the many more attendees. So what Professor Raghavan is here telling, she is absolutely right. We shall also try to present his lectures in a bigger forum, maybe in an international forums, and this IEEE as a separate body, as you know, it regularly do certain webinars, also international webinars for international communities and participants. So let us try from a different society, maybe IEEE Electron Devices Society, that if we can invite Professor Ravindra Mishra and spread this knowledge of Indian traditional Indian knowledge internationally, that will definitely look and will put a proposal to maybe to IEEE Education Society for such types of international seminars. So with this note, I officially conclude today's sessions, and thanks to Professor Mishra, Professor Raghavans, Professor P.K. Vasu, and all other distinguished speakers and the participants who are immensely benefited from today's lectures. So thanks to all of you. I express my good night to all of you. Thank you.
Thank you.